I started recording this session just to let everyone know. I had one query from uh, one of you around Blackboard. So Blackboard is up and running. All of you should have access to all your 4 courses that you're doing, all your 4 modules that you're doing this semester. And all academics are uploading their materials on a weekly basis to Blackboard. You should see previous lectures, tutorials, sometimes recorded videos like my course, my module, for instance, etc., etc. So if you don't see them, then let us know. I think I have uploaded all previous 5 weeks, as well as the book, as well as the tutorial that you should be finishing by now. So make sure that you go through them. Today, I'm going to talk about IP routing essentials. As I said during week 1, this module has 2 sides. One side is switching, one side is routing. We have gone through some switching concepts. We have seen VLANs, we have seen STP, for instance. We have seen technologies around either channel. Now, we're going also to see the routing side of the story. It shouldn't be a surprise for you, really, because since week 1, I gave you some homework, if you remember, with RIP, Routing Information Protocol, OSPF, Open Shortest Path,
Sorry,
FAIR,
sir.
and
Sorry
with
to
bear
sorry
with
to
me.
disturb you. I've raised my hand, but I think you can't see because you are doing the presentation. So basically, we can't access your module on Blackboard currently now. I think it's been like there for like 4 to 5 hours ago, as far as I'm concerned. So
Yeah, in the course it is not there.
only your module.
But I remember last week I asked a couple of you to check, and you
Yeah,
showed
it's
it
there.
to me.
It's
No,
there
it
last
was
week.
there, sir. It was there last week.
Yeah, sir. We can't show your module.
Let's see my module. Okay, let me check. Okay, let me check during the break. Yeah, that's why I said bear with me. Yeah. So you have done some work around OSPF, RIP, and EIGRP. Those are different routing protocols. Today, we're going to learn basically the fundamentals that all these routing protocols are aware of and they are working based on. So this chapter in particular is going to talk about the categorization for different routing protocols. Again, it shouldn't be something new, more of a recap of previous concepts that we've gone through. So when we say routing or routing or routing protocols, what we mean is how these routers advertise different subnets. We have different protocols operating differently, but at the end of the day, the aim is to distribute what we know as network layer reachability information, or these subnets or networks between adjacent routers. We're going to talk about path selection because these routers at layer 3 are going to find the best path from source to destination. When I say best path, each of these routing protocols has a different way of determining what is the best path. Yeah. What is the logic for best path selection? This is something to discuss now. And then the best path itself is going to be selected and is going to be installed in a table known as routing table. And this is how routers operate. They consult the routing table and then they send their packets accordingly. We're going to talk about static routing as well. So if you have done fully the lab that yesterday Anaida has run for you, at the end of the day, you were asked to define some static routes from one PC to another PC. You should be able to ping. And in order to have that, you need to define static routes on the router advertising 2 different subnets that you have. So we're going to see basic around static routing today. Last part of this lecture for this week is going to talk about virtual routing and forwarding, VRF, virtual routing and forwarding. So just for those of you who were there with us with VLANs, if you remember, I told you at the end of the day, you can get a virtual saw and cut down one switch into a couple of mini switches, but virtual mini switches, yeah? VRF is pretty much similar concept, but at layer 3. So for routers, you can also, instead of one physical router, define a couple of mini but virtual routers on the same physical router device. And this is what VRF is about. And it has certain advantages, in particular to do with security. And this is what the last part of this chapter is going to cover. So, not a surprise, router is supposed to send and advertise networks or subnets from different segments of a network to the neighboring routers. And then that helps when an IP packet comes into the router to make a forwarding decision based on the destination IP address of the IP packet. Router is going to consult against its routing table and find out what is the best path to get to that subnet, which is the destination for the incoming IP packet. We have different routing protocols. They are categorized into, from different viewpoints, they are categorized into different categories. Here, we're going to talk about what we know as distance vector routing protocols, as well as link state routing protocol. You have seen distance vector and link state previously as well. Another category that we have is path vector. So today we're going to see all these three main categories and how they are similar or different. With distance vector routing protocol, with this category, we also have another subcategory called enhanced distance vector routing protocol. And an example of that is EIGRP, which two students today are going to talk about EIGRP as well. So we know that the primary function of a router basically is to move the IP packet between segments, and routing protocols are there in order to learn different segment addresses and advertise those to each other. So when we say routers learn different segments IP addresses, we definitely mean non-attached links, yeah, because router, as soon as you go to the interface, you assign IP address and subnet mask, and you issue no shutdown, the router comes to know what is directly connected. But what routing, dynamic routing is about learning those remote networks. Thanks to these routing protocols, remote networks are going to be learned and advertised to the neighboring routers as well. So accordingly, we have two different types, static and dynamic. Yeah, static is the one that you say manually that this remote network is existing and this is how to reach it. Whereas dynamically is when routers themselves, they talk to each other, they negotiate, they learn networks with each other, and then they come to know what is residing where and how to get to that. So at the beginning of the process, usually what happens with dynamic routing protocols is that they're going to advertise the networks or segments that they are aware of to each other. And then from that moment on, they're going to send incremental updates. Incremental updates happens when there is a topology change. So a network is added, or a network is removed, or a new segment appears, or a link goes down, and therefore some destination networks become unreachable. So in all these scenarios, a topology change happens, and then routing protocols, they need to start informing each other about the topology change. So as I said at the beginning of the scenario, you're going to share, routers are going to share with each other the networks that they are aware of. And this is one step. Another step is that each router then is going to select best path to get to that destination network, to one single destination network. This is going to be happening individually and separately on each router as soon as they receive information about networks through routing updates. I already defined that for you, but here is the formal definition that when we are talking about routing, we can talk about two different things. We can talk about a collection of networks which are under the common or under a single administration, or when we are talking about one collection of networks under one single administration, which is now talking to another collection of networks, which is under a separate administration or under a separate control. So this is defined as AS, autonomous system. Therefore, you can have routing happening between routers within an AS, or you can have routing happening between routers, but between ASs, or between routers which are part of two adjacent or neighbor autonomous systems. So no surprise for you, hopefully, the dynamic routing protocols that you are aware of, RIP, routing information protocol, you have seen version 1, 2, you have seen RIP-NG for IPv6. Then we have EIGRP, Enhanced Interior Gateway Routing Protocol, OSPF, ISIS. OSPF and ISIS, they are similar in a sense that they are both categorized under link state routing protocol. And then you have Border Gateway Protocol, or BGP. So the first two protocols in this list, in this slide, they belong to distance vector category of routing protocol. Number 3 and number 4, they are linked state routing protocols, and the last one, BGP, is categorized as path vector routing protocol. So 3 main categories, as I said earlier, for routing protocols that we can have. When we are talking about routing happening inside an AS, and you know what an AS or autonomous system is, then you are talking about interior gateway protocols, IGPs in short. So IGPs are RIP, EIGRP, OSPF, ISIS. Whereas when you're talking about routing happening between autonomous systems, you are talking about EGPs, or exterior gateway protocols. Yeah, so that's the difference. And you can see here in the, can you see my cursor as well? Yes or no?
Sir, we can
Yes,
see.
sir.
So you can see here
Yes,
within,
sir.
thank you, within an AS, we have OSPF as IGP, EIGRP as IGP. Even BGP protocol has two different flavor. One flavor is called IBGP, another flavor is called EBGP. IBGP flavor of BGP happens to work inside autonomous systems, whereas EBGP flavor of the BGP is the only exterior gateway protocol, or EGP, which operates between autonomous systems. So what we mean when we say distance vector or link state. So when we say a protocol, a routing protocol is distance vector, we are referring to two terms. One is distance, another term is vector. Vector in this context is what we know as next hop. You remember we discussed with show IP route, you can see the content of a routing table. Part of the information that you had inside routing table, if you remember, was next hop. That next hop is called vector, and that's why we call this RIP or EIGRP, for instance, distance vector routing protocols, because they are telling us exactly what is the next hop to get to that destination. And then distance vector routing protocols, they see the destination and then they calculate what we know as metric. And this metric means distance here. So distance or metric is basically a value that tells us how efficient or how costly it is to get to that destination. So you see, both terms should make sense now. Why we call RIP a distance vector routing protocol. So if you remember, for instance, RIP is a very simple routing protocol. It operates based on the hop count, yeah, the number of hops that we have to get to the destination. So hop count is going to be the metric, or is going to be the cost, or is going to be the distance for any RIP router to calculate to see how costly it is to get to that single subnet, which is in a remote network. And then vector is the next hop router for the current router through which we can get to that remote network. So this is what we mean by distance vector. So similar to RIP, for instance, we receive periodic updates from our RIP neighboring routers, and then we're going to store the information in somewhere, and later you will see what I mean by that somewhere, because there is a specific terminology to define where that somewhere is. And then that RIP router is going to run an algorithm. With RIP, it's very simple. The algorithm is the lesser the number of hops to that remote network, the better. So the router chooses the best path as the path that has the lower number of hops to get to that destination. But with more advanced IGP distance vector protocols, you're going to run either Bellman-Ford algorithm or what we know as Ford-Fulkerson algorithm. Either of these two algorithms is going to be running on those routing updates that you have received, and then you're going to install the best path selected and calculated by Bellman-Ford, for instance, algorithm into your routing table. So you get all this information, you run algorithms over that information, and you select the best path and you install it in your routing database. Remember, the best path is the most economical path, yeah? And economical in this context is not always the shortest path, yeah? Depending on the protocol, it may be another metric considered rather than the shortest path. Well, OSPF, for instance, it goes with shortest path, no doubt there. But EIGRP, for instance, it uses what we know as a composite metric, which is a collection of metrics together, and that defines what we know as cost for or metric for EIGRP to choose what is the most economical path to get to that destination. However, all these routing protocols, they make sure that the best path is always loop-free. Yeah. So if I ask you in the exam, what is the one that is common? What is the one criterion that is common between all these different routing protocols and different routing algorithms in terms of path calculation or path selection? All of them make sure that you are avoiding loops. Yeah. So if you remember, with switching, we had STP for loop avoidance mechanism. Yeah, for layer 2 switching. Here with routing, we have routing protocols. Their job is to find the best path, but also make sure that the best path to get to the destination is going to be the loop-free one. Yeah. We previously said EIGRP is categorized on the distance vector routing protocols. That's correct, but to be more precise, EIGRP, unlike RIP, is categorized as an enhanced distance vector routing protocol. What we mean by enhanced, we will see shortly, but for now, One thing that you need to consider is what we know as convergence time. I think I have defined this previously in your lectures. Convergence time is the time that it takes for the entire network to reach a consistent view over all the subnets or over all the networks that you have in your scenario. Look at the example that you see here, for instance. You see this network, yeah? Where my cursor is, yes or no?
Sir.
Yes.
Yeah. So
Yep.
imagine that all these routers are running EIGRP. At the very beginning of the scenario, time 0, only this guy, R7, knows about this network. In time 1 or in time 2 or in time 3 or in time 4, usually over a few seconds, all these routers are going to start communicating EIGRP and sending EIGRP updates to each other, informing each other about the existence of this network. But how long does it take for all these routers to reach a consistent view over this subnet? Basically, how long does it take for everyone to know about this guy? That time is defined as convergence time. And why we called EIGRP an enhanced distance vector? This is simply because EIGRP compared with other IGP algorithms like RIP or OSPF is known to offer a faster convergence time when a topology change happens. Because if, for instance, this network goes down, meaning that, for instance, this link becomes unavailable, there is a topology change, and R7 needs to send immediately an EIGRP update to all neighboring EIGRP routers like R6, R2, and R1, saying that this guy is now disappeared. How long it takes for everyone to receive that update, process it, and then run the algorithm over the information that they have received and calculate new path to that network or to any other network, that is convergence time. And for EIGRP, this convergence time is known to be very fast, and that's why we call it enhanced. The algorithm, unlike RIP, is not Bellman-Ford anymore. It's not the shortest path anymore in terms of number of hops. Here, the algorithm for EIGRP is called dual. So DUAL, dual or dual. It's called diffusing update algorithm. Your course does not go through the details of these algorithms, but just to let you know that it's a different algorithm. And it's not going to be only a different algorithm, it's going to also be a different metric. So remember, we are talking about distance vector. Distance vector routing protocols like EIGRP, they need to tell us that in order to get to this network, what is the cost, and what is the cost, which is the distance, and what is the vector, and vector is going to be next hop. R3, you can see my cursor, yeah? R3 is saying that the way to get to the this remote network, which happens to be here, is to go through R1. That's why you see one arrow there, yeah? This is the vector. So we only say how to get to there through the next hop, and next hop is R1. For R3, next hop is R1. That's it. And then the metric, which is the distance, is going to be 8,000 something. And that 8,000 something comes from a combination of bandwidth, delay, reliability, load, and MTU. So if I ask you what is the cost for RIP algorithm, you say the number of hops. If I ask you what is the cost for EIGRP, you say the cost for EIGRP is a composite metric, which includes bandwidth, which includes delay, which considers reliability and load, and MTU as well. So 5 different elements together shape what we know as cost for EIGRP. You remember I told you a couple of times, and I think we had a question about this some weeks ago, that cost is going always to be distance and shortest path. And I told you, no, this is not right. It depends on the protocol. This is an example. So cost, for instance, for EIGRP is a combination of all these metrics together, and dual algorithm will be considering all these 5 together in order to calculate the metric. And the metric happens to be for R3, which is this guy, for R3 to reach to this subnet, which is here, 8,000 something, which is the most efficient one. That's why it's been installed in the routing table. So, and exactly because of this composite metric that we have for EIGRP, EIGRP is known as a hybrid routing protocol. They say sometimes hybrid. That hybrid refers to this composite metric that EIGRP has, unlike RIP and unlike OSPF. Another thing is that with EIGRP, and the reason that we call EIGRP an enhanced protocol, is that for some other routing protocols like OSPF, for instance, we need to send the entire routing table. Whereas with EIGRP, we're going to send an update only and only when there is a change. And therefore, we are not going to send a periodic updates. Remember with RIP, for instance, we used to send periodic updates. That's not the case with EIGRP. And that's why it's enhanced, because if you think about it, it's more efficient if you only send updates when there is a change in your network. Because if there is no change, there is no need for you to periodically send those updates. And another reason, again, for EIGRP, for EIGRP being an enhanced IGP or an enhanced interior gateway protocol, is the fact that EIGRP, unlike RIP, for instance, offers what we know as load balancing traffic. And load balancing traffic for EIGRP is advanced in a sense that it can be equal or unequal cost path. It can load balance traffic based on equal cost path or based on unequal cost path. What does that mean? If all these routers here are running EIGRP, then for R1 to send traffic to R2 or R7 or R3 to get to this network, EIGRP equal cost path allows you to send 33% of the traffic this way, 33% of the traffic that way, and 33% of the traffic this way. Whereas with unequal cost path also, it allows you to send 80% of traffic that way, 10% of the traffic that way, and another 10% that way. So either equal cost path or unequal cost path, whichever way you want, EIGRP can support it. We didn't have that with RIP, yeah? But we do have that for EIGRP. I think I have covered main points for fundamentals of EIGRP, but more about it, we will have it later during the presentations that two of you are going to make today. Any question, guys, so far?
Sir, can you again tell me about the equal cost path?
Yes, imagine that this router wants to send some traffic with EIGRP equal cost path. As the name suggests, it's going to be equal cost. So if let's say we have only 2 links, yeah, we don't have this link. So we have only these 2 links. We will send 50% of traffic this way and 50% that way. Both 50%. Together it becomes 100%. Equal cost. Each way is equal to another. You can have unequal cost path, whereby you send 80% of traffic this way and 20% that way. Make sense?
Yes, sir. So, sir, EIGRP uses the equal cost path.
EIGRP offers both equal as well as unequal cost path.
Okay.
The point is EIGRP offers load balancing based on both ways, whereas many protocols, they don't offer load balancing at all, or if they offer, they usually offer based on equal cost path, not unequal. And EIGRP is known as an advanced or an enhanced distance vector algorithm in a sense that it not only offers the equal cost path, but also offers unequal cost paths. Make sense?
Yes, sir. Thank you, sir.
So next one is linked state routing protocol. The very famous implementation of it is OSPF that you have previously seen. OSPF and ISIS. Your course is not going to go through the details of ISIS, but it does go through the details of OSPF. So you know what OSPF is, what it stands for. If you remember, I told you that OSPF is going to create a database. Basically, each router is going to have a local database of all known networks. And what happens is that all these routers at the end, at the very beginning of the scenario, as soon as these routers come up, they're going to share all the known networks with each other. That sharing happens through what we know as link state advertisements, or LSAs, as you can see in this slide. LSAs will be sent between all OSPF speakers. The idea is that all these information from all these OSPF speakers are going to be collated and put together in one database on each single router. Therefore, each router builds or creates or constructs a database of all known routes and stores them locally. So next step is that all these routers, now that they have filled up their local database with the entire view of the network, now they are going to run what we know as Digestra's algorithm. On each router, we're going to run Digestra on its local database. And each router is going to calculate what we know as the shortest path as a result of Digestra's algorithm on each router to find out what is the shortest path from each router to get to any of the advertised subnets. So I think the words like LSDB, linked state database, now makes sense what it does. Yeah. The Digestra, I already told you that is going to be run by every router and is going to calculate the best path, which with OSPF happens to be the shortest path. And as always, as I said before, with EIGRP, with RIP, with BGP, all these best paths must be loop free as well. So let's say here, R3, for instance, is aware of this way, and this way to get to R2, or this way, or this way, or this way to get to R4's 192.168.10/24 subnet. Let's say to get to this subnet, we may go through 2 hops, but with the cost of 10 plus 10, or we may go through this link with the cost of 50. So of course, the lower the cost, the lower the metric, the better. Therefore, even though it's just 1 hop, yeah, the shortest path happens to be through R1. So 10 plus 10 is lower than 50. Therefore, R3 is going to install this path inside this routing table to get to this subnet. Remember, we are talking about OSPF as a distance vector routing protocol, and therefore R3 will only need to show next hop to get to this subnet. So inside the routing table of R3 is going to say, in order to get to 192.168.1.0, your next hop is R1. That's it. Yeah. And then packet gets to here, and we have similar routing table here, and it tells you that in order to get to 192.168.1.0, your next hop is R4, which happens to be directly connected to this subnet. In this way, distance vector routing protocols can determine how to get to the destination. If it was RIP, yeah, routing information protocol, then the best path would be this one, yeah, because you have the least number of hops to get to that destination. Whereas OSPF says that the shortest path happens to be this way. Now, finally, what we have is path vector protocols, the third category of routing protocols that we have. The very famous example and the only existing example, I would say, for a path vector algorithm is BGP, Border Gateway Protocol. You don't see BGP in small or even large businesses as such. You see them mainly between very large businesses, between very large ISPs, and you see BGP as the backbone of the internet. So you know the internet, yeah? The internet is facilitated by a collection of all these autonomous systems across the globe. And what binds these autonomous systems together is BGP. So if you are working in an ISP, you have a very good knowledge and skills around BGP because this is the routing protocol that all these ISPs mainly dealing with. This one and also MPLS, but we don't cover MPLS yet. So we know BGP as a distance, as a path vector routing protocol. It is very similar to distance vector, but very not similar to link state. BGP is path vector in a sense that, well, we have vector, and the word again means next hop. We have that, but also we have a collection of other attributes that together are considered by a BGP speaker when they're going to choose the next hop and how to get to that final remote network. Attributes in the context of BGP are things like AS path. So AS path is one field inside all BGP update messages that it gets populated as you are sending the BGP update further and further. Another attribute is multi-exit discriminator, MED, we call it, origin, next hop, which is the usual suspect, you know it, local preference, and atomic aggregate or aggregate. I don't want you to go through those last fields or attributes for BGP, but for some important one like AS path attribute, origin, or next hop, you should know what they mean and how they are used. So let's see an example here. I think it's a good example. Each router in this example corresponds to one autonomous system. Yeah, so as you expect, BGP is operating between autonomous systems. So we are not inside one ISP. We are talking about communication between ISPs. So look at where AS1 is, or R1. Yeah. R1 knows about this network because this network is local to AS1. Now, R1 wants to advertise this network to its neighboring BGP speakers. So a BGP update goes this way to AS2. As this BGP updates goes to AS2 from AS1, inside the AS path attribute, number 1 will be added. Number 1 refers to AS1. BGP update for this subnet will be received here by AS2. Now, AS2 needs to send the same BGP update for 10.1.1.0 to its neighboring BGP speaker, which is R4 here. It sends that BGP update, but pay attention to this. Now the AS path attribute was updated, and now we have AS1 as well as AS2. So because we have traversed both ASs, we have also added both ASs into this BGP update message. Next, the BGP update gets to AS4, R4. Now it needs to be sent to the neighboring BGP router, which is AS3 or R3. You see this one now was updated with 1, 2, and 4. As you send your BGP update further and further, the entire path that this BGP update message has traveled through are going to be added to your AS path attribute of BGP update message. R3 receives this one and now needs to send it, let's say, to this guy and this guy, which are its neighboring BGP routers. It sends it back to AS2. What happens is this sign, which is the blocking sign. The blocking sign here, it tells you that this BGP update message will not be installed. Why? Because as this BGP update message will be sent this way, AS3 is also going to be added here. Now we have 1, 2, 4, and 3. AS2 can see its own AS number here. Therefore, there is no point in installing it because it causes loop. Yeah? And always remember I told you that routers not only select the best path, but also select the loop-free best path. And because we can see, I mean AS2 can see its own AS number in the BGP update message that it received, therefore there is a loop here. I'm not going to install this one on my router, which is R2. The same BGP update message will be sent that way, and again R3 will be added here. However, when R1 receives that BGP update message, is going to again discard it, is not going to install it. Why? Because inside the AS path attribute, R1 now can see its own number, which is 1. Yeah? 4, 3, 4, 2, 1. So I'm going to see my own AS number again here inside it. Therefore, I'm not going to install it because it causes loop. I know where this network is. I don't need to install it. So these two BGP update message will be rejected, will be discarded, while the others will be installed. And in this way, AS3, AS4, and AS2, they come to know where 10.1.1.0 is and how to get to that. So for instance, AS3 knows that through 421, which is this way, they can get into 10.1.1.0. Or AS2, for instance, knows that through just one AS, which is AS1, they can get to that network. Or AS4 knows that through 1 and 2, which is through this way, they can get into that network. Any question?
Excuse me, sir.
What?
This path vector algorithm, they have a specific path they follow, or they can recalculate later and change the path.
BGP, good question. So BGP, unlike any other routing protocols that you have learned so far, is known to be a policy-based routing protocol. You have seen a collection of attributes like AS path, like MED, like origin, like what else? Preference, yeah? All those attributes. These attributes, all of them together will be considered when BGP wants to send a packet or when BGP wants to update a route for basically routing a packet towards the destination. As I said earlier, BGP is the routing protocol that runs between ISPs. Between these ISPs, there is always one factor which determines policy routing, and that factor is money. So, for instance, imagine, Ibrahim, that this is, this is Sky, and this is 3. So 3 in the UK is one of the main ISPs or one of the main autonomous systems, not ISPs, and Sky is another ISP. If we don't want Sky and 3 to send traffic between each other for this network, we need to play with these metrics, we need to play with these attributes in a way that traffic goes this way for that subnet, not this way. Because they are not having contract between each other. They don't have customer agreements between each other to send and receive traffic. By the same token, if these 3 ISPs, for instance, they have a subscription to between each other, they have some contract between each other, they may use those attributes in a way that the traffic for 10.1.1.0 will be going this way, not that way. What I'm saying is that for RIP, hop count, for OSPF, shortest path, for EIGRP, the composite metric determine what the best path is. For BGP, it's money, it's our contractual agreements between ISPs that determine what is the best path. And what is the best path will be specified by these attributes. Make sense?
Yes.
That's why some of these attributes that you have with BGP, unlike other routing protocols, like origin, for instance, or like local preference, they can be modified by any ISP if it is more economical. And economical in this context, exactly what I mean is what the word means. So in terms of money, if it's more economical for them to send traffic that way. So let's say, to give you one better example, let's say Iran ISP, for instance, they have BGP running between themselves and Pakistan's ISP. Yeah. That connection with BGP is cheaper for Iran than sending the traffic to Turkey's ISP. If that's the case, if money-wise it's going to be cheaper for Iran's telecommunication ISP, for instance, to send traffic through Pakistan towards the destination rather than through Turkey, then Iran will select that path, and that becomes the best path. And how to make sure that all the traffic for certain networks is going to be routed through Pakistan rather than Turkey is exactly by playing by these attributes of BGP, giving more preference to one route, which is through Pakistan, over another route, which is through Turkey to the same destination. I think this is a good example that clarifies things with BGP. Yeah. So let's have 10 minutes break and everyone come back 10 past 3 and then we start again. Thank you. You can turn off your webcam and come back, no worries. So welcome back. Please turn on your webcam. Let's move on. In this section, we're going to talk about path selection. There are two concepts I want you to be aware of. One is RIB, RIB, routing information portal, routing information base, and another one is FIB, FIB, forwarding information base. What they are and what they do for us. So don't confuse RIP and RIP. Yeah. So RIP is the protocol. RIP is RIB, routing information base, is in fact your routing table. So what they are, forwarding information base or FIP gets its information from RIP, and RIP is in fact the routing table itself. We repeated quite a lot, and you know what routing table is. FIP is the one that actually does the forwarding for us. So FIP in fact happens after RIP information was received through routing protocols and routing table was updated. And then the RIP information is going to be fed into FIP or forwarding information base, which takes care of the actual identification of the path and does this by evaluating what we know as the prefix or prefix length, and then forwarding the packet. So the actual forwarding happens through FIB information, but FIB information is going to be programmed or is going to be fed by RIP information, which is in fact your routing table. So don't confuse these two information bases together. We're going to talk about concepts like prefix length, like load balancing in terms of unequal cost path or equal cost path, and administrative distance and metric. I think most of them should make sense to you because I have gone through them previously as we had some presentations with previous routing protocols, RIP, OSPF, so far. So prefix length is in fact your subnet mask. So you know a network like 1.1.1.0/24, the subnet mask is /24. So it is also known as your prefix length. So they are the same thing representing the same concept. So you know subnet mask is the number of bits that are set to 1 from left to right out of 32 places that we have with an IPv4 address. So subnet mask /8, it means that we have 8 ones from left to right in a string of 32 bits value. So 8 of them are set to 1 from left to right. Therefore, we show this with /8 if we want to go with / notation. All these routers and routing protocols, at the end of the day, they want to communicate subnets or prefixes, or in fact prefix length. So they want to communicate 1.1.1.0/24. So the network address and the subnet mask, or the prefix and the prefix length, whichever term you want to use. Then we have another concept called administrative distance. If you remember, we had a discussion with Hejra when she was presenting some time ago around what AD or administrative distance is. So basically it tells us how trustworthy a routing source is. So back to this example, for instance, if all these routers are running two routing protocols, not only one, OSPF as well as RIP as well as EIGRP, BGP as well as ISIS, whatever, but not one routing protocol, two protocols. Therefore, all these four routers, they're going to learn about this subnet on the right-hand side by two means or through two ways. How one way is more trustworthy than the other way is what administrative distance or AD tells us. So according to AD, we can choose one path that we have learned through one routing source than the other path to the same network that we have learned through another routing source. Yeah, this is what AD tells us. Another concept that we have for selecting the best path is, of course, metric. And you know, metric is in fact your cost, and you're after best path. Therefore, you're after the best cost for your preferred route to get to that final network. Metric is different from one protocol to another. So for RIP, is going to be hop count. For OSPF, it's going to be the shortest path with the minimum cost. And then for EIGRP is going to be a composite metric, if you remember, bandwidth, load, reliability, etc. So depending on the routing protocol, the type of the metric is going to be different. However, whichever routing protocol that you are running in a scenario, the lower the metric, the better. Or the lower the metric, the more preferred the route is. What we expect from outcome of a routing protocol is to build a routing table similar to what you see here. So inside routing table of a Cisco router that you can see its content by issuing the command show IP route for IPv4 or show IPv6 route for IPv6 networks, you should see a collection of subnets, and each of these prefixes and prefix lengths together, they are going to specify a range of IP addresses that you see. So these are CCNA1 concepts. If you don't know what I'm talking about, if you don't know how you can get this range out of this prefix, that simply means that you need to watch those videos I've shared with you as soon as possible. And then we are talking in the context of distance vector routing protocols, and therefore we always have next hop. So how to get to this prefix, you go to that next hop. And then the outgoing interface, which is the physical interface or the physical link on the local router through which we can get to this next hop. So outgoing interface corresponds to next hop. Outgoing interface is the egress point, we call it, that through which we can get to this next hop, through which we can get to this prefix. And this is how we interpret the content of routing table. There is one rule which is always true and is always checked before any other rule. I'm talking about path selection. You know that we need a couple of rules that we need to consider. One rule is AD, administrative distance, yeah? And I told you that some routing sources are more trustworthy than others. For instance, static routes are more preferred over OSPF. And therefore, if we want to get to the subnet, to a subnet through static route or through the ISIS or OSPF or EIGRP, whichever, because a static route has a better administrative distance, which means a lower value, by the way, therefore we're going to go to that subnet through our static route. and we're going to ignore or disregard other routing sources like EIGRP, ISIS, OSPF, etc. This is one rule. Another rule is that within the same routing source, imagine that all the routers in our scenario are OSPF and they're running OSPF. If within the same scenario, if I have two paths, one through R1 to get to this subnet from R3, and another one through this way to get to this subnet from R3, I'm going to consider metric, and the lower the metric, the better. Therefore, within the same routing source, which is OSPF in this case, I'm going to send my traffic this way, not that way. So this is another rule. So two criteria so far you have learned about how routers and routing protocols select the best path to get to a destination. But also there is another rule, and that rule basically simply tells us that if we have a couple of same networks, so 10.0.3.0, all of them are the same, but with different prefix length or with different subnet mask, so /28, 26, or 24. Always, the more specific prefix length is going to win the competition. Therefore, if this is my router, I receive a packet for this network, but the destination has the subnet mask /28, which is more specific than /26 or /24. I'm going to send out my packet through this way, through Gigabit Ethernet 1/1, not through 2/2 or 3/3. So again, another rule, and that's the third rule that you have learned now, is that a more specific prefix length is preferred. So three rules we have learned so far. The lower the AD, administrative distance, the better the route. The second rule is the lower the metric, the more preferred the route or the path is. And the third rule is that if we are talking in the context of the same prefix or the same prefixes or the same networks, then the path for more specific prefix length is going to win and is going to be more preferred. So remember these three rules. Move on to administrative distance. I told you what administrative distance is, and this table is telling you that what the default values for administrative distance for different routing sources are. If a subnet or a network is directly connected to the router, the administrative distance is 0. And therefore, you can see that it is the most preferred route because we are directly connected to that subnet. We don't need really to route or forward that packet because it is directly connected to us. And that's why you see the lowest value for administrative distance is for directly connected subnets. If I know a subnet through static route, then the AD is 1. EIGRP summary route, the AD 5, EBGP 20, EIGRP internal 90, OSPF 110, RIP 120, EIGRP external 170, and internal BGP or IBGP we know it 200. Therefore, if I ask you in your exam, for instance, that I know about this subnet through EIGRP as well as RIP, which path should I select? The one that I have learned through EIGRP? Or the one,
EIGRP.
yes, the one that or the one that we have learned through RIP. EIGRP should be preferred. So when routers send routing updates to each other, regardless of the type of routing protocol that we are talking about, the person that is going to receive that information is routing information base of the adjacent or neighboring route. Whether the RIP installs that preferred route or the path that was selected in the routing table or not depends on this. if the route that we get in the update for that routing protocol does not exist at all in our routing table, RIP or routing information base is going to install it, is going to accept it, and is going to install it within its routing table. If the route that routing update is telling us already exists inside our routing information base, therefore we have some information about that remote network, we now compare administrative distance. If we have lower administrative distance for this advertised route, then we're going to install it because we have a better path to get to that remote network. If we don't have a better path, meaning that the AD or administrative distance for the update that I have received is higher than what we already have inside our routing table, then we are not going to install it, we're going to just reject it. So I think it should be very simple and should make sense. Another example with administrative distance, just pay attention to the table. So for the same network, remember, whenever we are talking about administrative distance in the context of administrative distance, we always need to talk about the same remote destination, but different routing sources, as you can see. So the same network was advertised through 3 different routing protocols, one EIGRP, one OSPF, one ISIS. And my router has received update from EIGRP, from OSPF, or ISIS for the same network. Which one should I install inside my routing table, or what we know as routing information base? The one which has lower AD, which is 90. We also had with protocols like EIGRP, what we know as load balancing or multipathing. It can happen through equal cost or unequal cost. For IGPs, so exclude BGP now for now from this discussion. For IGPs, they always prefer, of course, the internally learned routes over external routes. And the way that they do it is, in fact, by using lower metrics, because lower metrics for IGP protocols are preferred. Remember the rule that I told you, those 3 rules? One of them was about AD, another one was about metric. So the lower the metric, the better. So they are going to, first of all, send traffic internally, not externally, if they can. And then within different IGP protocols, which one we should choose? We should choose the one that we are running but has lower metric. That one is going to be chosen. So I think the best way is just to go through the example. So in the routing protocol that you can see here, we are running. O here stands for OSPF. So this example, all these 4 routers are running OSPF. In order to get to this remote network, I can have from R1, I can have this way or that way. Metric is going to be 20 if I go this way, and it's going to be 20 if I go that way. You see, when I have equal metric values, I am able to send 50% of the traffic this way and another 50% of the traffic that way. So in fact, this provides me a mechanism in order to increase my bandwidth across multiple paths. I don't need necessarily to send all the traffic this way or that way. I can use multipathing, but with equal metrics, I'm going to use equal cost multipathing, sending 50% of the traffic that way, another 50% of the traffic that way. For multipathing and equal cost multipathing, you should have the same value for metric. And then if you check your routing table, you should see something like this. This network, this subnet here, is accessible through 2 routes, not one. Yeah, and both of them were installed in the routing table. Remember, not all routing protocols support multipathing or load balancing. EIGRP, for instance, it supports. OSPF, for instance, it supports. Yeah. With OSPF here, this 110 is AD, is administrative distance. Go back to this slide if you remember. OSPF, the administrative distance is 110. So inside your routing table, for each route, you see one bracket, and inside bracket, you see 2 values. They are separated by a slash, yeah? The first value is always AD, administrative distance. The second value is metric. So this number 30, by the way, is wrong. Make sure that you put it in your notes. It should be number 20, yeah? So the metric from R1 to get to R3 for this network is metric, the value is 20. So this is wrong. This is a typo here. So disregard this and consider 20. So inside the bracket, the first number is AD. The second number is the metric. And the metric here is 20. Again, we have 110. And again, the metric here is 20. You see, in order to get to the same destination, I have 2 paths. The first one is going to be through 10.12.1.2, which is probably this guy. And the second one is 10.14.1.4, which is possibly this guy. So 50% of the traffic can go this way. Another 50% can go that way. This is equal cost multipathing. Once again, for this to happen, you should have exactly the same metric value here. And that tells the router that you can send 50% of the traffic on the first route and another 50% through the second. I can have same example, but let's say this time with EIGRP routing protocol, whereby I now have unequal cost load balancing. What does that mean? The metric, if you see, is different. And the protocol this time, in this example, is EIGRP. So in routing protocols, inside routing tables, for protocols like OSPF, the way that you show it inside the routing table is that you have O at the beginning. With RIP, you have R. With EIGRP, they don't use E. Instead, they use D. And this D stands for dual, if you remember, the algorithm that EIGRP is based on. That's why if you see D entries inside your routing table, you're talking about EIGRP. Now, in order to get to here, EIGRP has 2 ways or multi-paths. First path is through this way, and second path is through that way. How is the contribution in terms of bandwidth through each of these 2 ways? Well, the contribution is exactly the relation between these 2 numbers. So if you create a fraction, put 30,326 on top and 5,632 at the bottom, that fraction of the traffic will go this way, and the remaining is going to go that way. This is exactly how unequal cost load balancing or multipathing happens. In order to change the metric value to make it unequal, what they have done in this figure, in this slide, is that they have changed the delay for this link to 10 microsecond, and for this one also to 10 microsecond, and therefore they have caused the composite metric to change. So if you remember, the EIGRP protocol, it uses composite metric, and inside the composite metric values, we have delay value as well. So if you change delay on the links, then the metric is going to be changed, and then that's why you can see 2 different values for the metrics. But the way that multipathing works is exactly the same as equal cost multipasses. Instead of having 50% of the traffic, 50% that way, you're now going to have less traffic going this way and more traffic going that way. Yeah. So that's fundamentals of routing that we've gone through. I just need to cover quickly static routing. I think you have done static routing yesterday, according to what Anaida told me. Correct me if I'm wrong.
Yes.
Good.
Yes, sir.
So therefore, this section shouldn't be really challenging for you. So you have previously seen one very famous example of a static route, and that's the default static route. You remember the quad zero network? It's inside the videos that I shared with you as well. So 0.0.0.0, of course, /0. IP route command to that quad zero network is an example of the default static route and is used to basically refer all the refer to all the unknown destinations. So if the current router has information about, let's say, only 5 remote networks, but you want still to have connectivity for the rest of the networks through your closest router, which is your default gateway, by the way, you are going to add quad zero network with static route, which is called default static route. On that router, you put IP route 0.0.0.0, and then you put subnet mask, and then you specify next hop, as well as your outbound egress point on that route. We're going that is the very famous example of a static route, but we're going to see different types of the static routes as well. In addition to that, in this subsection, we're going to see directly attached static routes. We're going to see recursive static routes. Then we're going to see fully specified static routes, what they are, how they are similar or different. We have some scenarios that we don't use dynamic routing protocols like RIP, OSPF, ISIS, EIGRP, or BGP. Sometimes we don't use them because we don't have enough hardware resources. Sometimes we don't use dynamic routing protocols because we want to make sure that certain paths are always selected and chosen. We don't want to leave things for automatic behavior of routing protocols. Back to this slide where I talked about distance, administrative distance for different routing sources. You can see that static routes are pretty much preferred over the rest of the routing protocols, over all the dynamic routing protocols, because they have administrative distance of 1. So if you know about if you know about one network through 2 sources, one being a static is always going to win the competition. So, and we're going to use this preference for certain scenarios. We don't want sometimes to leave everything for dynamic or automatic behavior of the routing protocols. 3 types, as I said, for static routes. In fact, it should be 4 types because default static route is another example, but it's not in this slide, but just bear of it and have that in your mind. So if I issue IP route command to define an static route to somewhere, but I only add the next hop interface. This is known as directly attached static route. So the command that I need to use to define a static route, or what we know as directly attached static route, is this, the one that I have highlighted. Can you see the highlight as well?
Yes, sir.
Yeah. So IP route, network subnet mask, and then you provide IP address for the next hop interface only. This is called directly attached static route. Let's see what we mean. Let me bring this picture to the next slide, and hopefully it should make sense. So if I go to R1 and then I issue IP route 10.22.22.0, which is this network, and I only specify, yeah, serial 1/0 as the next hop, or the outbound interface to get to the next hop. Then I am talking in the context of directly attached static routes. I do the same on R2. So on R2, instead of this, of course, I refer to this. So I say IP route 10.11.11.0, serial 1/0. So I'm saying to R2 that if you want to get to this network, this is your outgoing interface. And I'm telling R1 that if you want to get to this network, this is your outgoing interface. This is known as directly attached static routes. How can I see it? How can I verify my configuration? If I go and issue show IP route, which tells me the content of my routing table, then I can see on R1, for instance, I have 2 C entries and 1 S entry. C entries stands for directly attached networks. So 10.11.11 is directly attached to R1. 10.12.2 is directly attached. Yeah, both of them are here. But I also see 1 S entry in my routing table, which is to do with my static route for directly attached network that I just defined. So 10.22.22 is accessible through serial 10. This is the outgoing interface. So serial 10. So this router from now on is able to ping this network. Previously, without this static route command, you were unable to ping from R1 to any IP address within 10.22.22.0/24. Does that make sense?
Yes, sir.
Everyone?
Yes, sir.
Good.
Sir.
Similarly, here on R2, show IP route 10.11.11.0/24 is now accessible through this guy, which is serial 1/0. If you think about it, what happens, just go back to the previous slide. If you think about it, what happens in this routing table is a recursion or a recursive lookup. Those of you who are aware of any programming language, you should know what recursion means in the context of programming languages. Here I am in R1, and I have information about 10.22.22/0/24. I am saying that this subnet is accessible through serial 1/0. But router needs to find out what serial 1/0 is, yeah? Because this is just a label. But router is a layer 3 device which works with IP. How to find out what the IP for this serial 1/0 is? Router now checks this entry recursively. You see the second line here, yes or no?
Yes.
Yes, sir.
Yes.
Sir.
And serial 1/0 here tells the router that this is the guy and this guy is directly connected to you. So you see a recursion happens there as well, yeah? Now let's see what we mean by recursive static routes if we don't specify the subnet ID and instead we specify next hop IP. So previous command that we had for a static route, let me bring it up, otherwise it becomes confusing for you. So the one that I have, the one that I have highlighted here is the previous command. Can someone tell me what is the difference between this command and this command? So what is the difference between directly attached static route and recursive static route? Raise your virtual hand if you know the answer. I don't see.
Sorry, sir. Can you repeat the question, please?
Yes, just before I repeat the question, where are the webcams? I only can see 9 people. So thank you, Yogesh, Shamsur, Gulam, Faiza, Ashish. Where are the rest? Do I need to say one thing 1,000,000 times, guys? So the question is this. Previously, you have learned directly attached static roots. And this is the command that you can see in the slide is highlighted. Now, I am telling you that there is another command for what we know as a recursive static root. And this is the command which is on the top of what I have highlighted. Can someone tell me what is the difference between these two when you read the command itself? You see my slides, don't you?
Sir, in static IP,
Raise your hand, please. Raise your virtual hand, and I want everyone to check this one. So the question makes sense or not? I have provided two commands for you. I'm saying what is the difference? One is directly attached static root, another one is recursive static root. Ghulam, go on.
sir, on the first side, the static IP route pointing about the interface, and the second one is recursive static routes. It's pointing on the hoop IP.
Next hop IP. Yeah, that's great. Well done, well done, well done. So this guy, which is the previous thing that we have learned, which is in fact the directly attached static root. If you remember from here, we were specifying the outgoing interface, or we were specifying what we know as egress point. Yeah, we were saying that to get to this network, this is how you need to, this is the exit that you need to take. Now, with the recursive one, we specify exactly the IP of the next hop, which happens to be this guy for this subnet, if you want to get to that network from here, or it's going to be this next hop for this subnet if you want to get to it from R2. Make sense? Let's see the command itself. Here, we have the same network, exactly same network, and we are going to do the same scenario. We are going to advertise this subnet for R1, and we're going to advertise this subnet for R2. This should be R2. How we do it? IP route, and then the remote network, and the subnet mask for it, and then we specify next hop IP rather than interface ID. So for R1, which is this guy, to get to this network, the next hop IP is this IP. And for R2 this is R2, this is a typo here. So for R2 to get to this subnet, next hop IP is going to be this guy. We don't use the egress point anymore. We use next hop IP address. Why? If you remember here with directly attached static routes, I told you that at the end of the day, routers, they need to do one recursive lookup because they don't know the IP of serial 1/0. They need to go and consult their routing table to find out what is the exact IP to which they need to send packets destined for 10.2022 and 22.0/24. So therefore, here with recursive static routes, we say, you know what? I don't want you to go and start searching for what serial 1/0, for instance, is. I tell you exactly what the IP is for next hop. Therefore, if you have a packet for this network, right away send it to this next hop IP. You don't need to go and do lookup as such. Yeah, so the recursive already gave you all you need. And the third way of defining a static routes is fully specified static routes. And fully specified static routes is this command. Basically, as the name suggests, it's fully specified, meaning that you not only specify the egress point or the outgoing interface ID, but also you specify what the next hop IP is. And this way, or fully specified static route, is known to be more efficient than any other way, because you give the router all the information that you need, that the router needs, and all the information that you have. Therefore, in the same example, if I bring this one to here, you're going to go to R1 and you're going to say, you know what, R1, in order to get to 10.22.22, you need to leave this interface and your next hop IP is this. This is called fully specified. So all information is provided. Exit point or egress point, as well as your next hop. And you tell R2 that to get to this subnet, your exit point or your egress interface label is going to be this, and your next hop IP address is going to be this. Is that clear?
Yes, sir.
That's good. So another concept that we have, now that you have learned the static rules, default static route, and then how to specify, define static routes, either using the directly attached ones or recursive static route or fully specified static route. Another concept for you to learn is floating static route. Pay attention to this diagram. In order for R1 to get to this subnet or to know about this subnet, R1 can go through this way and can go through this way. Looking at the link type here, what is the link type for this shown by Z? Those who have done packet tracer.
So it's a serial
Serial cable.
port
That's
cable.
good. That's good. So here we are talking about serial cable type. This one is a gigabit Ethernet link. Yeah. Which one is faster, serial or gigabit? Anyone?
Gigabyte.
Serial is
Serial is the lowest one, and gigabit or fast Ethernet are faster than serial. Now, the point is this. You have two paths or two ways to get to this destination. What if I want to say to R1, for instance, that R1, you know what, for normal traffic, send it this way because it's faster, but have this way also installed in your routing table through static routes, but use this one as a backup solution. Therefore, if this guy goes down, if this link disappears, or if this link is broken, from that moment on, this link is going to be utilized. Therefore, this link is going to be a secondary solution compared to this primary solution. How we do that? We assign a value at the end of the IP route command that we use for static routes. Basically on R1, we say in order to get to 1020 network, your next hop is this 10.12.1.2, which is this guy, gigabit 0/0 on R2. But the administrative distance now is going to be manually overridden, or is going to be overwritten by you, and is going to be assigned to 10. Remember, the default administrative distance for a static route is 1. But now you have overwritten that to 10. Then you add another command and you say IP route for this network with this subnet, so it's the same network, is going to be through serial 1/0, which is this way. But you give it a less attractive administrative distance, which is going to be a higher value than 10, any value. It can be 300, it can be 400, it can be 12, whatever. So a higher number, which makes it less attractive to the primary solution or to the main link that you have. From this moment on, if router wants to send packet, will always use the first primary solution, not the secondary solution at all. They don't do even load balancing because they are different routes, different administrative distance. However, if the primary route goes down, the secondary route is going to come up and become active. Another type of static routes is called static null routes. Null interface is an interface uh, which discards the packets. If you define on a router, if you define one interface as a null interface, what happens is that if you send any packet towards that null interface, packets are going to be discarded. There is a use case for using and specifying static null routes. The use case is here. So look at the subnets that have been assigned between these two routers and this one and this one. This company, well, the name is ABC, whatever, they have 3 subnets defined here. Yeah. All of these subnets can be summarized into this IP address. If you don't know what route or address summarization is, again, this is because you haven't watched the previous videos that I have shared with you. So on this ISP router, we're going to define a route and we're going to say, you know what, send all the traffic for this summary route that way, not this way, because this address summarizes all these internal LAN addresses or even link addresses for company ABC here in this example. Now, the issue is that whenever this guy on R2, let's say, whenever this guy on R2, which is this router, is going to send ping packets or trace route packets for this IP address, because we have defined a summary route, that address refers to 2 things. That address refers to probably one machine from this range, which is 172.16 range, and also matches the summary route that we have. And therefore, you can see that half of the traffic will be going this way, another half will be going that way. Yeah, which is not good, because it's as if you are sending half of your traffic correctly to the destination and you're discarding another half. And therefore, we need to get rid of this. And therefore, on R1, which is our border router, we say, you know what? I know that we have already defined a summary route, which is 172.16.0.0/20, but if you have an actual IP packet which matches this destination network, which happens to be all the previous trace routes that you had, by the way, send it to null 0, because this is a summary route and and there is no actual machine there under this IP address, because it's a summary route, and therefore we don't want any packets to be routed for this, therefore discard them, therefore send them to null 0. How we do that? I think it's not here, but in the book you can search for it, and they tell you the exact command. Basically, you put null 0 at the end of the command that you have. I think I have mentioned this before, but just to let you know that any IPv4 command that you enter also has a sibling in IPv6. So IPv6 is not a separate story. It's exactly the same story, but you just need to say IPv6 instead of IPv4. So IP route, you say IP route in order to define the static routes for IPv4. Now you say IPv6 route, and then you define IPv6 static route. This is the prefix with IPv6, and this is the prefix length. Unlike IPv4 that you say 255.255.255.0, basically you show the subnet mask in dotted decimal notation. With IPv6, we use prefix notation, prefix length notation, which comes in the form of a slash notation. So /64. And then you specify next hop, which is IPv6 next hop address. For instance, on R1, in order to advertise this IPv6 prefix, you use IPv6 root command, and then the next hop is going to be 2001 DB8 12::2, which is this guy. This is going to be next hop IP address for recursive static root for IPv6. One thing though that you need always to do with IPv6, you remember some of you have presented previously to me and to the class, basically rip ng. One of the very initial commands that you need always to run, regardless of the IPv6 subtopic that we are discussing for IPv6, is always you need to enable IPv6 module on any Cisco devices, and that happens with this command, IPv6 unicast routing. This is the only additional command. Whenever it comes to IPv6, you need to put it and you need to insert it. So IPv6 unicast routing always need to be enabled before you define IPv6 static. I'm going to leave you to self-study virtual routing and forwarding. It's not going to be difficult if you just go through the slides. Just go through it. Let me know if it doesn't make sense or if you have any query around it. Now, I talked for 2 hours, which is too much. Now it's time to see what you have done.
So I have a question.
Go
So on slide 12, you told us about the 3 same networks with different subnet mask.
Atmospheric distance, yeah.
Yes, and you told us that more specific subnet mask or prefix length will going to be win. So what do you mean by the more specific? Is it like classless or classful subnet mask?
No. More specific prefix length. Let me bring it back. You see the slide?
Sir.
Can you see the slide? Yes, no?
Yes.
Yes, sir.
Good. So here, so forget about classful and classless. Classful and classless, if you watch those videos, you know that classful addressing has been obsolete. We don't have classful addressing anymore. Here,
sir.
what we are talking about is that for the same network ID, which is 10.0.3.0, I have 3 separate routes inside my routing table. One for /28, one for /26, one for /24. Look at the IP addresses ranges that I have for these 3 subnets. The point is this: if I receive a packet with for 10.0.3.0 network, or for this destination, which of these 3 routes I should choose? I said when you have such a situation, this is where the more specific prefix length is the winner. And as I have suggested, as the slide says, the longest prefix length is always preferred. More specific means what? /28 is more specific than /26. /28 is more specific than /12. Because if you think about it, 32-bit subnet mask from left to right, the number of ones becomes this /28. You're saying that you have 28 ones out of 32 from left to right.
Yes, sir. Now I got
Yes.
it. Yes, sir.
Yeah?
Now I got it. Yes.
Good. Any other question? So let's move on to Hassan Iftikhar and Ahmed Abdullah. I think you are presenting EIGRP today, yeah?
Our topic is OSPF.
My bad. Shuaib is presenting. And Sukant Roy. Shuaib, Stripe here. Stripe is not here. I need to make him absent. Stripe.
He's here. He's here.
Hi, Tribe. Have you